The size of the grounding conductor in the raceway between the current transformer and the main distribution panel follow this procedure. Firstly, determine the amperage of the largest overcurrent device protecting the conductors in the raceway. This is typically the main breaker in the main distribution panel. Secondly, identify the grounding system for the facility. This information can usually be found in the electrical drawings or the electrical inspection report. Thirdly, reference National Electrical Code Table 250.122 to determine the required size of the grounding conductor based on the following factors: the amperage of the largest overcurrent device and the grounding system. Fourthly, use the bullseye diagram. This diagram provides a visual representation of the grounding system and helps to ensure proper bonding. The bullseye is the central point where the neutral and equipment grounding conductors are connected together. Fifthly, in the bullseye diagram, connect the following conductors: the neutral conductor from the service entrance to the main distribution panel enclosure, the grounding electrode conductor, or UFA ground, to the main distribution panel enclosure, and the equipment grounding conductor from the raceway to the main distribution panel enclosure. Sixthly, size the grounding conductor in the raceway based on the requirement determined in Step 3. The size of the grounding conductor can be calculated using the following formula: size in American wire gauge is equal to 2 times the American wire gauge of the largest phase conductor plus 1. For example, if the largest phase conductor is 200 amps and the grounding system is a non-isolated UFA ground, reference table 250.122, which indicates that a number 6 American wire gauge copper conductor is required. Let's apply this example using the formula: size in American wire gauge equals 2 times 4 American wire gauge plus 1 equals 6 American wire gauge. Therefore, a number 6 American wire gauge copper grounding conductor is required in the raceway between the current transformer and the main distribution panel. Let's delve a bit deeper into each of these steps. When determining the amperage of the largest overcurrent device, it is crucial to consult the electrical panel schedule or the overcurrent device itself. The amperage rating will be clearly marked on the breaker or fuse. Ensure that you are identifying the overcurrent device that provides the primary protection for the conductors within the raceway in question. In identifying the grounding system, look for specific details regarding the type of grounding electrode used, such as a ground rod, ground plate, or concrete encased electrode, also known as a UFA ground. The presence of a separately derived system should also be noted, as this can affect the grounding requirements. When referencing Table 250.122 in the National Electrical Code, be aware that the table provides minimum sizes for equipment grounding conductors based on the rating of the overcurrent protective device. It is permissible to use a larger grounding conductor than what is indicated in the table. However, the table specifies the minimum acceptable size. Additionally, pay close attention to the material of the conductor, whether it is copper, aluminum, or copper-cut aluminum, as the table values will differ depending on the conductor material. The bullseye diagram, although not explicitly defined in the National Electrical Code, is a conceptual representation of the grounding and bonding system. It highlights the importance of a central grounding point where all grounding and bonding conductors converge. This helps to minimize voltage differences and create a low impedance path for fault currents to return to the source. The connections made at the bullseye are critical for electrical safety and proper system operation. The neutral conductor, grounding electrode conductor, and equipment grounding conductor must be securely and reliably connected to the main distribution panel enclosure. These connections should be made using listed connectors and according to manufacturer's instructions. Proper torquing of the connections is essential to ensure a low resistance connection. When calculating the size of the grounding conductor using the formula, it is important to understand the relationship between American wire gauge sizes and ampacity. As the American wire gauge number decreases, the conductor size increases, and the ampacity also increases. The formula provided is a simplified method for determining the appropriate grounding conductor size. However, it is crucial to verify that the calculated size meets the minimum requirements outlined in Table 250.122 of the National Electrical Code. In the example provided, a number 6 American wire gauge copper grounding conductor was determined to be the appropriate size. This size is based on a 200 amp overcurrent device and a non-isolated U for ground. It is important to note that this is just one example, and the appropriate grounding conductor size will vary depending on the specific installation conditions. It is also worth mentioning that the National Electrical Code permits the use of equipment grounding conductors run inside or outside of a raceway. If the equipment grounding conductor is run outside the raceway, it must be securely fastened to the surface on which it is carried. Additionally, the equipment grounding conductor must be protected from physical damage. When selecting an equipment grounding conductor, consider the environmental conditions in which it will be installed. If the conductor will be exposed to moisture, corrosive substances, or extreme temperatures, it is important to choose a conductor that is suitable for those conditions. In some cases, it may be necessary to use a special type of insulation or conductor with a protective coating. Grounding and bonding are essential for electrical safety. By properly sizing and installing grounding conductors, you can help to protect people and equipment from electrical shock and fire hazards. Always consult the National Electrical Code and other applicable standards when designing and installing electrical systems. In addition to the steps outlined above, there are a few other important considerations when sizing grounding conductors. Firstly, it is important to ensure that the grounding conductor is properly labeled and identified. This will help to prevent confusion and ensure that the grounding system is properly maintained. Secondly, the grounding conductor should be installed in a neat and workmanlike manner. This will help to ensure that the grounding system is reliable and effective. Thirdly, the grounding conductor should be inspected regularly to ensure that it is in good condition. Any damaged or deteriorated grounding conductors should be replaced immediately. Also consider the impact of voltage drop on the grounding system. A long grounding conductor can experience significant voltage drop, which can reduce its effectiveness. To minimize voltage drop, use a larger grounding conductor or shorten the length of the conductor. Consider the use of supplemental grounding electrodes. In some cases, it may be necessary to install additional grounding electrodes to improve the effectiveness of the grounding system. Supplemental grounding electrodes can be used to reduce ground impedance and provide a lower resistance path for fault currents. Ensure compliance with all applicable codes and standards. Grounding and bonding requirements are constantly evolving, so it is important to stay up to date on the latest codes and standards. The National Electrical Code is the primary source of information for grounding and bonding requirements in the United States. Let's discuss some advanced considerations in grounding conductor sizing. Firstly, harmonic currents can significantly impact the performance of grounding conductors. Harmonic currents are non-sinusoidal currents that can cause overheating and increased voltage drop in grounding conductors. If harmonic currents are present in the electrical system, it may be necessary to increase the size of the grounding conductor to mitigate these effects. Secondly, electromagnetic interference, or EMI, can also be a concern in electrical systems. Grounding conductors can play a role in reducing EMI by providing a low impedance path for unwanted noise currents to flow back to the source. Proper grounding and bonding techniques can help to minimize EMI and improve the performance of sensitive electronic equipment. Thirdly, surge protection devices, or SPDs, are often used to protect electrical equipment from voltage surges caused by lightning or other transient events. Grounding conductors are an essential component of an SPD system as they provide a path for surge currents to flow to ground. The grounding conductor must be properly sized and installed to ensure that the SPD can effectively protect the equipment. The selection of appropriate connectors and terminations is crucial for ensuring a reliable grounding system. Use listed connectors that are specifically designed for grounding applications. Ensure that the connectors are properly installed and torqued according to the manufacturer's instructions. Proper termination techniques are essential for creating a low-resistance connection. Periodic testing and inspection of the grounding system are essential for ensuring its continued effectiveness. Ground impedance testing can be used to measure the resistance of the grounding system. Visual inspections can be used to identify any signs of damage or deterioration. Any issues that are identified during testing or inspection should be addressed promptly. The location of the grounding electrode system can also impact its effectiveness. The grounding electrode system should be located as close as possible to the service entrance and should be installed in an area with low soil resistivity. Avoid locating the grounding electrode system near underground utilities or other metallic structures. Proper documentation of the grounding system is essential for future maintenance and troubleshooting. Keep records of the grounding electrode system location, conductor sizes, and connection details. This information will be helpful for future electrical work and can aid in identifying potential problems. Understanding the different types of grounding systems is crucial for proper grounding conductor sizing. The most common types of grounding systems include solid grounded systems, impedance grounded systems, and ungrounded systems. Each type of grounding system has its own unique characteristics and requirements. It is important to select the appropriate grounding system for the specific application. Proper grounding conductor sizing is essential for ensuring electrical safety and system performance. By following the steps outlined above and considering the advanced considerations, you can help to create a safe and reliable electrical system. Always consult with a qualified electrical professional when designing and installing electrical systems. Remember that grounding is not the same as bonding, although they are often used together. Grounding is the connection of an electrical system to the earth, while bonding is the connection of metallic parts of an electrical system to create a low impedance path for fault currents. Both grounding and bonding are essential for electrical safety. Another important consideration is the use of equipotential bonding. Equipotential bonding is the practice of connecting all metallic parts of an electrical system together to create a common electrical potential. This helps to minimize voltage differences and reduce the risk of electric shock. Equipotential bonding is particularly important in areas where people may come into contact with water, such as bathrooms and swimming pools. In addition to the National Electrical Code, other standards and regulations may apply to grounding systems. These standards may be specific to certain industries or applications. It is important to be aware of all applicable requirements and to ensure that the grounding system complies with all relevant standards. Finally, remember that grounding is an ongoing process. The grounding system should be regularly inspected and maintained to ensure that it continues to function properly. Any changes or modifications to the electrical system should be carefully evaluated to ensure that they do not compromise the grounding system.